So in this video we're going to look at Maclaurin polynomials. So before we jump into Maclaurin polynomials, I want to recall two things. So recall that the linear approximation is going to be f prime of x naught times x minus x naught plus f of x. And the quadratic approximation, now g, is going to be the second derivative of our center over 2 x minus x naught squared plus f prime of x naught, x minus x naught, plus f of x naught. And the idea with this is in the linear approximation, the tangent line, this makes sure that the value is the same. In the quadratic approximation, this makes sure that the value is the same. It goes through that point. This makes sure that the slope, the first derivative, is the same. Now, for a line, we only have the first derivative and the value. For the quadratic, we have a second derivative, so this makes sure the second derivative is the same. And both of these are just special cases of a Maclaurin polynomial. So a Maclaurin polynomial is a polynomial that has the same derivatives up to some derivative, whatever power the polynomial is, I'll say up to k, as the function at x equals 0. So Maclaurin polynomials are all, we're going to say, centered around 0. When we get to Taylor polynomials, that's more general, where I can move the center. But what this means, so if my Maclaurin polynomial is p sub k of x, that's the kth degree Maclaurin polynomial, this requires that p sub k of 0 is going to equal f of 0. P sub k prime of 0 is equal to f prime of 0. The first derivatives match up. The second derivatives match up. And all the way down to a stopping point of the kth derivative, evaluated at 0. And like with these, a linear approximation is good very close to the point. Quadratic is good for a little bit longer because it takes into account more information. The Maclaurin polynomials can be exceptionally good at approximating the value. And when we see a first example, I'll show you what happens as we get a higher and higher degree Maclaurin polynomial. Now, the next question you might have is, how do we write this Maclaurin polynomial? So we know that the polynomial p sub k of x is going to be a naught plus a1x plus a2x squared all the way up to a sub k x to the k. And I just need to figure out what the coefficients are, and it can be found this way. So the nth coefficient will equal the nth derivative of the function evaluated at 0 divided by n factorial. Now, let me say here, I mean that the 0th derivative is just the function, the value of the function. That's what, not x. That's what that notation means. Now, you might be asking yourself, okay, it makes sense that I'm going to do these derivatives because as I take the derivatives, I'm going to make that work out, but why do I divide by n factorial? And the idea is this. If I did not divide by n factorial, we know that the first derivative of x is just, of x is just 1. Well, 1 factorial is 1, so that doesn't change things. The second derivative of x squared is going to be the first derivative of 2x is going to be 2. The third derivative of x cubed is the second derivative of 3x squared is the first derivative of 6x is equal to 6. And what's happening is the nth derivative with respect to x of x to the n, I'm going to take the n to the front, then the n minus 1, then the n minus 2, all the way down to 1. It'll end up being n factorial. So to rectify these polynomial derivatives with what that order derivative we want, I need to divide by n factorial. So if you have this, the process we're going to see is I just find the derivatives I need to find and the value, and divide by n factorial. So let's see a couple of examples. Find the fourth degree Maclaurin polynomial of f of x equals e to the 2x. So fourth degree means that I need f of x, f prime of x, f double prime of x, the third derivative of x, and the fourth derivative of x. Well, f of x is e to the 2x. The first derivative is 2 e to the 2x. The second derivative is 4 e to the 2x. The third derivative is 8 e to the 2x. And the fourth derivative is 16 e to the 2x. I stop here because it's a Maclaurin polynomial. It's not what we'll see in the next video, which are series, which we just find a pair and keep going. Okay, now I evaluate these at 0. I don't usually show all of this notation because it's there's a lot of wasted writing there. Well, not wasted. It's good to have it to be valid, but you're going to be doing the same thing again and again for all the Maclaurin polynomials, so it might be smarter to come up with a process to organize yourself that isn't rewriting a bunch of f's. So when I put in 0, I get 1, I get 2, I get 4, I get 8, I get 16. And again, I don't usually write all this stuff. I write about this and then I use arrows to get to the next thing, but to show it validly, this is going to get me to A0, this is going to get me to A1, this is going to get me to A2, this is going to get me to A3, and this is going to get me to A4. And I'll show everything here so that it's clear where everything's coming from. So for A0, I take this term divided by 0 factorial. Now, 0 factorial is defined as 1, so that's why it works out. For this one, I take 2 divided by 1 factorial. It's the first derivative. 1 factorial is 1 as well, so I get 2. For this, I do this term, 4 divided by 2 factorial. 2 factorial is 2. 4 over 2 is 8. No, it's not. Sorry. 4 over 2 is 2. For this, I take that value divided by 3 factorial. 3 factorial is 6. 8 over 6 is 4/3. And the fourth derivative is 16 divided by 4 factorial. Well, 4 factorial is 24. So I have 16 over 24. These both reduce out by a factor of 8, so I get 2/3. Okay, and finally, so these are my coefficients of x to the 0, x to the 1, x to the 2, x to the 3, x to the 4. So my polynomial, p sub 4 of x will equal 1 plus 2x plus 2x squared plus 4/3 x cubed plus 2/3 x to the 4th. Now before I go on, I want to just go back a slide and wrap up. So we see the coefficients. It is definitely worth noting that the terms, and this will make a big difference when we get into later things, and we saw it in that last one, the terms then will be the nth derivative evaluated at 0 divided by n factorial times x to the n. So we sort of know that already, but it's worth keeping in mind later on when I start asking where do these things converge. Okay, another example, or actually let me show what happened here graphically before that. So here, this blue curve is e to the 2x. This red line is the linear approximation, where it has the 1 and it has plus 2x. Now, if I increase this, I'll add on more of the terms. So this is just the first degree. It has the constant in the first. If I go up another one, if I add that 2x squared, watch what happens to my red curve. It gets closer to the blue curve farther out. Okay, and so this was 1 plus 2x plus 2x squared. And as I keep on adding more, so this was the second degree, if I get to the third degree, I get that 4/3 x cubed, and it looks like this. And you see, it's an even closer approximation to my curve. And if I go up to the fourth degree, the one that we have, I add on that 2/3 x to the 4th, it gets here. Now you can see this is getting exceptionally close to the curve, about sort of between, let's say, negative 0.6 to positive 0.6. As I add more and more terms, so this is the polynomial we currently have. As I add more and more terms, it gets to be better and better. So watch, I'm just going to go up, I think I add up to 20 terms in this file. So you can see it just keeps getting better and better and better. Now, it still is bad over here, but if I add more and more terms, because this series actually converges everywhere, the polynomial will eventually equal e to the 2x. Okay, so that was this. Next example. Find the 5th degree Maclaurin polynomial for f of x equals sine x and use it to estimate the value of sine of 1. So let me go through this, hopefully a little bit more quickly. We know the process, so I need the derivatives all the way up to the 5th derivative. So f of x, f prime of x, the second derivative, the third derivative, the 4th derivative, and the 5th derivative. And we know that the derivatives go sine, cosine, negative sine, negative cosine, and then back to sine, and then cosine. So that's all up to the 5th derivative. Let me try to model the color scheme I had. So I went purple, blue, green. Okay, so blue next. Now I need to find all of these evaluated at 0. And so this is the notation I usually use. Again, it's not great. It doesn't explain as much. If I wanted to show it explicitly or without any explanation, I would write what I did before. But to save myself some time, I just sort of do this. At x equals 0, so I'm evaluating all these at 0. I get sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, cosine of 0 is 1. And then I will go to green, and so the coefficients, and you can see it's just a little bit less writing. I don't need to write all these f's, which sort of wastes time. So 0 divided by 0 factorial, and I'll write it one more time here. So we get 0 factorial is 1, 0 divided by 1 is 0. I have 1 divided by 1 factorial, 1 factorial is 1, 1 divided by 1 is 1. 0 divided by 2 factorial, 2 factorial is 2, 0 divided by 2 is 0. negative 1 divided by 3 factorial, well 3 factorial is 6, negative 1 over 6 is negative 1/6. 0 over 4 factorial, 4 factorial is 24, 0 divided by 24 is 0, and 1 divided by 5 factorial, well 5 factorial is 120, 1 divided by 120 is 1/120th. So these are the coefficients, 0, 1, 0, negative 1/6, 0, 1/120th, and this lets me get to my 5th degree Maclaurin polynomial, so P5 of x. I have no constant, it's 0. I have 1x, I have no x squared, I have negative 1/6 x to the 6th, no, sorry, x to the 3rd, it's a lie. Okay, I have no x to the 4th, and I have plus 1/120th x to the 5th. And then if I want to use this to estimate sine of 1, then I can just do the 5th degree Maclaurin polynomial evaluated at 1, which will be approximately sine of 1. And so that's going to be 1 times 1 minus 1/6 times 1 cubed plus 1/120th times 1 to the 5th, which is going to become 1 minus 1/6 plus 1/120th. The common denominator here is 120, which means I need to multiply this by 120 over 120 and this by 20 over 20. So I get 120 over 120 minus 20 over 120 plus 1 over 120. And this will give me 101 out of 120. Okay, which is actually a pretty good estimate of sine of 1. And I'm going to show it graphically, even though I could put in the calculator and see that it's close. So graphically, let's see what just happened. I might change my function from e to the 2x to sine of x. Okay, and I want to go to the 5th degree. Now we're at the 1st degree right now. Notice, when I go to the 2nd degree, since the a2 was 0, I had no x squared term, it doesn't change my polynomial. But when I go to the 3rd degree, it adds on that negative 1/6 x to the 3rd, and we get this, and it's a better approximation. And then 4th degree, I didn't have a term, but when I add the 5th, I add on the 1 over 120 x to the 5th, and we get this. And you can see, look right here, look how close this is to the blue and the red, the sine of 1 and this 5th degree polynomial of 1. So it's exceptionally close, which is really nice to have. Okay, now that's graphically what happens there. It's kind of a fun graph. So this is the 5th degree. If I extend this out to the highest degree that I have, you can see it just gets better and better. We have polynomials dealing with this transcendental function, and that's incredibly powerful. Okay, one last example. So these first two, we had to actually go through this process of taking the derivatives and putting stuff in. Sometimes on like the AP test, I see problems that look like this. And these are actually a little bit easier. So here's the idea. They're giving me pretty much all the information I need. This should have, a 0, fn of 0 in the work. I just need to go through the process. So I need f of 0. Let's see, I need the degree 3, so I need f prime of 0. I need, this should be an f here. I had the 2nd derivative evaluated at 0, and I need the 3rd derivative evaluated at 0. And I apologize for the 2 typos in the problem. I should have paid more attention. F of 0 they give me, okay, so that's just 5. But then you're like, okay, how do I get f prime of 0? Well, that's the 1st derivative, which means that n is 1. So I put in 1 plus 1 factorial, n being 1 up there, divided by 1 minus 1 factorial. 1 plus 1 factorial is 2 factorial. 1 minus 1 factorial is 0 factorial. 2 factorial is 2, 0 factorial is 1, so this gives me 2. I do the same thing. The second derivative is just where n is 2. 2 plus 1 is 3, so I get 3 factorial in the numerator. 2 minus 1 is 1, 1 factorial in the denominator. 3 factorial is 6, 1 factorial is 1, I get 6. And when I put in 3, 3 plus 1 is 4, so I get 4 factorial in the numerator. 3 minus 1 is 2, so I get 2 factorial in the denominator. 4 factorial is 24, 2 factorial is 2. 24 over 2 is 12. And now I can go to my terms. So this should be 5 over 0 factorial, which is just 5. This is 2 over 1 factorial, which is just 2. This is 6 over 2 factorial, which is just 3. And this is 12 over 3 factorial. 3 factorial is 6. So this should give me 2. And what this means is my third degree Maclaurin polynomial of x is going to be 5 plus 2x plus 3x squared plus 2x cubed. And I can, let me grab a new color, evaluate this at -2 to approximate f of -2. And that's going to be 5 plus 2 times -2 plus 3 times -2 squared plus 2 times -2 cubed. 5 minus 4 plus 12 minus 16. So I have 17 minus 20, which gives me -3. So that's what p sub 3 equals. That means that this is approximately equal to that. Alright, I hope that helped out. I'll come up with a video shortly about Maclaurin series in general. Feel free to comment below if you have any questions.